Okay, so here's another example of a disaccharide, and we're going to do the same thing that we did in the previous example. We're going to look at the disaccharide, we're going to break it apart into the two monosaccharides. We're going to label the monosaccharides that basically make this disaccharide up, and then we're going to describe the glycosidic bond that happens in between the two sugars. So the first thing that I like to do is just maybe make you pay attention to the glycosidic bond. And the glycosidic bond is happening right here in blue. So this is the link that connects these two monosaccharides up. So this is the glycosidic bond that I need to eventually describe, or the glycosidic linkage that I need to eventually describe in the actual question. But before we get to that, we need to figure out what type of sugars we have first. So again, we take a look at the sugar that's written to the left, or in the previous example it was written to the top, and we have to identify that one. And then we'll take a look at the second monosaccharide, and we'll identify that one as well. So we're going to do the same thing that we did before. I'm going to take this first ring structure, and I'm going to kind of convert it over to a Fisher projection because I think it's easier to identify that way. And here I see the anomeric carbon. So this is the carbon that's hooked up to the oxygen that was an OH group, right? So that means that this very first carbon, because there's no other carbons attached to it as an attachment out here, so that very first carbon had a C double bond OH group. So the C double bond O was broken, and that opened up this glycosidic bond for it to connect. And we've got one carbon, 2 carbons, 3 carbon, 4 carbon, 5 carbon, and 6 carbons in total. So I'm just going to draw a line, CH2OH, and there are 4 carbons in the center, giving us a total of 6. I now need to go through, just like before, and look at the OH groups and the positions of which they're pointed. So this OH group is pointed down, so that means it goes right-handed. This OH group is pointed up, so that means it goes left-handed. This OH group up, so that means it's left-handed. And then I get this carbon that had an OH on it, but that OH has been converted to an oxygen because that's the connector of the ring. So where did this OH go? Well, once again, we assume that all of these sugars are D sugars unless we're told something different. So it automatically goes to the right-hand side. So this is the sugar Fisher projection, at least, of the sugar in question. So I need to go to the chart, and I need to find the aldose chart because this is an aldehyde, and I need to look for a 6-carbon sugar that has an OH that goes right-handed, left-handed, left-handed, right-handed. And when I find that, I'm going to see that this thing is called D-galactose. Okay, so the sugar to the left in question is D-galactose. Now I need to do the same thing to the sugar that's over on the right-hand side. So I'm going to do basically the same procedure here. This is 1 carbon, 2 carbon, 3 carbon, 4 carbon, 5 carbon, 6 carbon, right? So there's 6 carbons there. So I know I'm going to start with a carbon up here at the top, and I know it's eventually going to go to a carbon down here at the bottom. I know that this 6th carbon is a CH2OH group, right? So CH2OH here. Well, where is the number 1 carbon? Well, that's always the anomeric carbon. So the anomeric carbon is right there. It has an OH group that's free on it. And this anomeric carbon I know is the anomeric carbon because that's the one that the oxygen has hooked up with to make this ring structure. So that means that this is a C double bond OH group as well. So this is another aldose. Again, I would know if it was a ketose because there would be like another CH2OH group here, and there's not. No CH2OH group is drawn. So I know that this is not a ketose that I have on my hands. It's a aldose instead. Now, this OH bond is not really pointed up and it's not really pointed down. Sometimes in the pictures or the questions, what they'll do is that they'll just draw it straight out to the side like I did here to let you know that that really position's not important at this time. Or sometimes what they'll do is they'll do a squiggly line. And this squiggly line will let you know, well, it could go up or it could go down. It doesn't really depend because we're not really focused on that. So if you do see that in the questions, that is what that means. So we know 2 carbons have been drawn, and we now have 4 carbons that are involved now. This is the first carbon, so this is where my C double bond O was. So we've taken care of that one. That double bond O has been broken to form an OH group in the ring and allow carbon to connect to the oxygen on that particular carbon 5. On the second carbon in, this OH group points down, so this is right hand. And third carbon, the OH points up, so this is left hand. On this carbon, it's kind of strange, right? There's no OH group. This is where my glycosidic linkage is. But take a look at the way that this bond is drawn. This bond is basically drawn in the downward position, right? So this is kind of giving you insight that this OH group was pointed down as well. So if the OH group points down, then that means it goes right hand. And then this carbon had the oxygen in the ring. Well, we've said that was the OH group before, and we always assume that that last one is right-handed unless we're told something different. So there's the structure of the sugar that's involved in the second monosaccharide unit. So I need to look for an aldose, and that aldose needs to have the OH group that goes right hand, left hand, right hand, right hand. And when I find that sugar, I will figure out that that is called D-glucose. Again, one of those that you should memorize. Okay, so this is a D-galactose connected to a D-glucose. And those are the 2 sugars that are involved in this disaccharide. What kind of glycosidic linkage do I have? Well, this was my anomeric carbon. This is regarded as carbon 1 because this is carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. Up here at the top, I do the same thing there. This is my anomeric carbon, so this is carbon number 1. That's where my aldehyde group was. So this is carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. So the glycosidic linkage happens between carbon 1 and carbon 4 on the other molecule. So 1, 4 prime. This is an anomeric carbon, which means that's connected to the oxygen of the ring, and the position of the OH group is very important there. This position of the OH group basically is pointed up. So if I go back and take a look at whether that's called alpha or whether that's called beta, I'm going to find out that any OH group that's pointed up is going to be called beta. So this is a beta linkage, so I'll put the beta out in front, and this is a beta 1. Now what about the 4 prime? I mean, it points down, so should that be given the alpha? And the answer is no. And you're probably going to question, well, why? We did that in the last one. Why don't we do it here? Well, that's true. But the difference is that in the last example, the glycosidic linkage happened between the 2 anomeric carbons. And here, that's not going on. It's happening with this anomeric carbon, which is why we said this was beta 1. But this is not an anomeric carbon. Right? This is not the carbon that's connected to the oxygen that also had the C double bond O group on it. That was the definition of the anomeric carbon. So this is our anomeric carbon right here. And only the anomerics get alphas and betas. That's it. All the other sugars, they don't get alphas and betas. Only the anomer does. So that means that this number 4 carbon, because it's not the anomer carbon, I should not give it an alpha and I should not give it a beta. I'll leave it alone. So this is a beta 1-4 prime glycosidic linkage. So we understand that the beta goes with number 1, and the 4 prime goes with the second group. Now I put parentheses here. I guess I shouldn't have put those there. So that way it's very clear that beta goes with number 1. And instead of a hyphen here, they tend to like parentheses there. So beta 1 parentheses 4 prime, and we know that it's a galactose, and we know that it's a glucose. What is this disaccharide called? This is something that you know as lactose. So all of you people out there that are lactose intolerant, this is the sugar that you're staying away from. So there's something about your metabolism process that doesn't really break down lactose like it should. And because it can't break down the lactose, your tummy gets upset and your intestines begin to cramp. When you drink a glass of milk, or when you eat a piece of cheese, or when you basically engulf something that's made of some type of dairy product. For those of you that have kittens and puppies at home, especially nice little cats, we think that we're doing them such a nice favor by leaving them out a bowl of milk so that they can lap it up at all hours of the day. The problem is that dogs and cats are lactose intolerant. So if you're giving them basically milk, you are basically giving them tummy troubles, and they begin to have diarrhea, and they begin to basically get bloating and cramping that happens. So stay away from the milk when you give it to your pets. The problem is that during them, while they are a kitten or a pup, or while they're at a young age, still nursing off of the mother, they can digest the milk. However, if you have not given them milk for their entire life, they become lactose intolerant. So they do have a tendency to basically get rid of the enzyme that breaks down lactose. And then if you go for a year or 2 years without giving them milk, when you give them milk after that, well, they're lactose intolerant already. They can't break it down anymore. The same thing happens with people as well. If you take a look at different nations and you look at their diets, well, we in the United States grow up eating cereal every morning, and we grow up drinking a glass of milk with our meals. For some of us, that's okay. So we continue to drink milk and we continue to eat cheese even after we have finished nursing. Right? So we don't really become lactose intolerant. Some of us do, but many of us do not. However, if you look at another country like Japan, where dairy is basically non-existent in their diet, while they are a child or while they are an infant, well, they need the lactose. But after they get to a certain age, the dairy is removed from their diet and the enzyme goes away. And many people in Japan are lactose intolerant for that reason. So this heat map is basically a map of the world, or Earth at least, and we see the multiple countries that are listed. The darker the color, the more lactose intolerant people that live there. So if you take a look at the United States, of course, the United States is down on the 0 to 20% range. We typically tend to keep milk in our diet from a very young infant age all the way up until we turn adults, and all the way up until the point that we die. The truth of the story is, however, is that the older that we get, the more prone our body is to become lactose intolerant, which is why you see all of these lactose-free products that are out in the grocery store now. Not only that, if you go onto these diets that limit your dairy, because a lot of times dairy has a very high fat content, so it's not uncommon to basically see these diets out there that strive you away from carbohydrate, that also strive you away from dairy product. And when you do this, you are basically instigating your body to start getting rid of this enzyme and allowing you to become lactose intolerant. So at the end of this diet, there is a possibility that you maybe could never have any dairy anymore. So you just got to be really careful with what you put into your body and what you eat on a daily basis, and know the actual consequences of that much later down the road. As you can see, China, Japan, some parts of South America, Asia, all of these are countries that have very high lactose intolerance. And that's why when you go to these Chinese restaurants or these Thai restaurants or the Japanese restaurants, you're actually seeing them not use any kind of dairy at all. If you do see some type of milk that's being used on the actual recipes or included as an ingredient in the recipe, it is not dairy milk. Most of the time it is a coconut milk that they are using, and that of course is completely different. So lactose, dairy, all of these are being removed from their diet at a very young age, and because of that, their body just really destroys the enzyme for breaking down lactose called lactase, and they cannot break down this sugar. Disaccharides cannot go into the bloodstream. They have to be passed through the intestinal tract. Hence, that's why you get the bloating and the upset stomach and the diarrhea and everything else that comes with it. So that's the story with the lactose intolerance, and I hope you pay attention. And if you do become lactose intolerant, don't say I didn't warn you.